Our next speaker did not really like this weather, so he has decided to stay in Singapore. We will have Reza Shokri talking to us about auditing in the privacy machine learning space. Reza is a presidential young professor in the computing department at National University of Singapore, where he also leads the Data Privacy and Trustworthy Machine Learning Research Lab. He is currently exploring trustworthy federated learning, privacy-aware model explanations, and privacy-preserving data synthesis. He regularly collaborates with Intel, Google, and Meta on these topics. Reza.
Hello, everyone. Thanks for inviting me to this great summit and great to be with you all remotely. And thanks for the introduction. Today, I'm going to expand a little bit on some of the points that Katerina mentioned in the last slide about how to reason about privacy risks. So when the slides are ready, then would be happy to elaborate more on this. Okay. Right, so today I'm going to talk about privacy auditing in general for algorithms and an algorithmic approach to privacy auditing with the focus on machine learning. So what I want you all to remember from this talk later on is that there are different interpretations of privacy. In particular, there's a difference and distinction between confidentiality and privacy in the kind of risks that they define. And we will talk about how risky machine learning algorithms, especially large machine learning algorithms, are with respect to personal data, and motivates why we need quantitative measures and algorithmic approaches for auditing data privacy for these algorithms and for machine learning. And the good news is that there is actually a systematic and quantitative method which is widely accepted today as a standard way to quantify privacy risks of machine learning algorithms when it comes to training on personal data and sensitive data. And there are also tools, and there's a popular open source tool that I will introduce that can help organizations and researchers to audit privacy in machine learning. Next slide. Yes, so the privacy regulations and policies have identified the importance of the problem of assessing privacy risks and coming up with techniques that can mitigate those risks. In particular, GDPR, multiple articles talk about data protection impact assessment, and this is very important. But what happens is that the focus in practice is mostly on data collection and data sharing and access control, which is who has access to data, whether the data has crossed certain boundaries, and whether those who have access to data are using the data in the right context in which the data was shared, which is a very important consideration. But to better understand the broader aspects of privacy risk in algorithms and in machine learning, I need to split the risk into two categories. One is what I called the direct privacy risks. And again, in a framework of a machine learning system, this is where an entity has access to users' data. So the training data, for example, is stored in a particular place, or the queries from the users of a system would be processed by some entity. And we want those entities to have the rights and the correct privileges to access the data. And we don't want unauthorized entities to gain access to that. So if that happens, then I would call it a direct violation of data privacy or direct privacy risk on user data. Here, the mitigation techniques involve confidential computing, using secure multi-party computations, trusted hardware, using access control techniques, and so on, which to prevent an unauthorized entity to gain access to the data. Something which is a little bit more subtle is the indirect privacy risks of algorithms. And that is when an entity, an authorized entity, has access to the output of an algorithm. So for a machine learning algorithm, the output is a model, right? So we run a training algorithm on some private data, we output a model, and that model would be able to do, let's say, predictions on generate data and so on and so forth. We do want our users to use the model, to have access to the model. We deploy these models on products, and we want to know whether there is any risk involved with respect to the training data. The problem would arise when an entity, by having just simple access to the model or its predictions, would be able to reconstruct information about the private data. If that happens, this is what I call the information leakage about the data, or the indirect privacy risk of a machine learning algorithm. We don't expect that happen. If it happens, it's unintentional, because we don't want the model to reveal information about the specific data points in the training set. We want the model to extract general patterns about the data. But unfortunately, this is not happening this way, and the models contain a lot of, and they encode a lot of information about individual data records in the training sets, and this could be exploited. And this is a huge risk, because if you imagine, if the training data is sensitive and we don't want any unauthorized entity to gain access to that data, we also want to make sure that any entity who works with the output of the algorithm would not be able to reconstruct that information, and that is the concern. So in practice, we have shown, and some other researchers have also shown, that these risks are real. By having simple API access to some machine learning as a service platforms, we showed a few years ago that you could identify the training data that it was used to train the model. And imagine that you have a mobile app, and then you are using some service like that, and then the users, the legitimate users of your system, would identify what data you use for the training set. If a model is released, again, a few years ago, researchers have shown that in the case of large language models, that you can generate some sensitive information which was verbatim from the training set, or something a bit more sensitive. If you have a language model and then you modify it or fine-tune it with sensitive data, for example, clinical BERT, which was trained on clinical notes, we showed that it's very easy for an adversary to identify the sentences, the points that were in the training set. This is a huge concern, and these are real models, real applications out there. These are not hypothetical scenarios. Or in the case of federated learning, which was also mentioned, federated learning, first of all, itself is not a privacy-enhancing technology. It's just a way to train a model in a collaborative way without sharing the data. So in federated learning, we want to prevent the direct privacy risks. So I'm not sharing the data with you, but together we share some models that are trained on our data, and we aggregate it using some servers, and then we train some model globally. So direct privacy risk is taken care of, but indirectly through sharing the models which are trained on our data locally, we have shown that adversaries, the server who runs the service, or any other participant would be able to extract significant amount of information about participants' data, to the extent that they can reconstruct data that was used in the other clients' training sets. So all that means that if we are training models on personal data, the models are personal data, and they need to be treated like that. If a data cannot cross a boundary, the model which is trained on that data cannot cross a boundary neither. If someone does not have authorized access to the data, should not have authorized access to the model, unless these risks are properly mitigated. So what we want first is to have a standard model to quantify these risks in such a way that when we apply mitigation techniques, we can be confident that these risks are taken care of. We need a meter, we need the quantification framework, and this kind of auditing cannot be done by looking at the process, right? These are not process-based auditing techniques. These are more quantitative, and I want to highlight that multiple times. So in order to quantify privacy risks of, let's say, machine learning algorithms, I want to construct a hypothetical game here for you to better explain how we go about quantifying privacy risks of algorithms. So imagine a world in which we have a training set and we train a model on that using a particular algorithm. And then there is a parallel world in which we do exactly the same thing, but we add a data point to that training set. So the training set remains the same, except that there is one additional data point. We use exactly the same training algorithm, and we train a model. Now, the difference between these two worlds is just the addition of this data point. It could be a single data point, a bunch of data points. It doesn't matter that much. It could be, for example, a sentence, a paragraph, a document, organization data. But the difference is in one unit of data record. Now, the question that we are asking is, if we imagine a hypothetical adversary who wants to exploit information leakage of the algorithm, and if we place that adversary in either of these worlds with perhaps 1/2 probability, right? So by chance, he could be in this world or in that world, and we ask the adversary whether he would be able to tell in which world he is in. Okay, this hypothetical, super powerful adversary has to guess. And this is the basic question that we ask. Is it possible for an adversary to differentiate between these two worlds? And we admit that if that is possible, if an adversary with high confidence can do this detection, then the algorithm has leaked information about that data point, because that was the only difference between these two. And the technique that we use, because we need to now simulate that hypothetical adversary, the technique that we use is called membership inference. So membership inference is an algorithm, a problem that's given a model trained on some data set and a particular data point that we talked about, that additional one, for example, whether we would be able to detect that data point was a member of the training set of the model or not, right? And now we want to measure to what extent accurately we can perform this task. So membership inference is somehow equivalent to this the kind of re-identification attacks, but in the context of machine learning. So, and the success rate of this attack, as I mentioned, would be a good indicator for leakage and privacy risk. Here I want to just very, very briefly illustrate what an adversary would do, and then we get into the metrics. So imagine we have a data universe, right? The data points distributed according to some distribution in this universe. A subset of this is selected as training data. We train a model on that. Adversary observes the model. And what he does is that actually comes up with an algorithm that transforms and maps this data into some, let's say, one-dimensional space that according to his algorithm, the ones on the left are highly possible to be members of the training set, and the right are the non-members. He can choose a threshold and say, okay, I define these as member, but he's going to be correct on some of his guesses and he's going to be right in some others. So he makes an error and he has some correctness. That in this two-dimensional space would reflect the performance of this analysis. And if the adversary, let's say, is less conservative or more conservative and varies the threshold, he would get different values there, right? So this risk profile that we see here, every point on that risk profile, it says, oh, there exists one adversary with, that would be able to recover this fraction of the training data, the personal data, but at the same time is going to make some error, right? So what is the recovery? What fraction of the training data he could identify? What is the error? How many non-members of the training data he falsely thought that they are member, right? So these two together would reflect the privacy risk of the algorithm. And this would enable us to do a very nice and actionable assessment of the privacy risk. So here we see the plot again, and this is very important. We see that for the x equal to y line, that is corresponding to the case where the adversary has no idea in which world he is in, right? So this means that we did not manage to identify any information to exploit in order to infer what data points were in the training set. Okay, so the diagonal line means no risk. But then as we move towards up and left, we can partition the space into low risk, medium risk, and high risk algorithms. And let's see what exactly these dimensions mean again. I repeat, the error means how many data points, or what fraction of the data points which are outside the training set, we would falsely believe that they are members of the training data. And the power of the attack means what fraction of the training data we would be able to identify and recover. So if an algorithm is having the profile, we have this dotted line profile as an example in the red area, as an example of an algorithm. And actually many of these large language models are very similar to that. They are very high risk. When we go towards the left, it means that the adversary would be able to single out individuals without much error. If he points that Alice was in the training set, he is right with high probability. When we move to the right, if the plot in the curve is towards the right, means that there is more blending with the population. There is more anonymity, right? Even though the adversary might identify, let's say, Alice to be the member of the training set, but he falsely believes, Bob and Charlie and so many others are in the training data. So this profile could help us to take actions. We have a model we want to deploy, and what we do is that we just go and run this assessment. We check in what regions more or less they fall, and we see whether it's safe to deploy the model, or we need further investigation, or it's too risky and we should not deploy. So this assessment could be done before we apply some mitigation techniques and after that. And this is this is a very standard way of analyzing privacy risks. So AI regulations guidelines from a few years back until now, they have highlighted the importance of this risk, the importance of this re-identification risk in machine learning and membership inference attacks. And there has been lots of efforts towards designing sharper techniques, more powerful techniques for quantifying privacy risk in machine learning for all different types of data. And also we designed and developed over the last 2-3 years an open source tool, which is called ML Privacy Meter, and accessible to everyone, which exactly does that. So here we try to operationalize the requirements by the regulations using the standard computer science techniques for quantifying the privacy risks in machine learning. And it's great to know that today many large organizations are using this tool and or have their own internal tools being developed following the templates and the procedures in this tool. So if you are a privacy manager or a product manager, and you have been wondering how to assess privacy risk of the algorithms, you can start here. There are many examples of applying this tool in different contexts. So, for example, of course, this is not a sensitive data set, but this is the TED Talks, annotated speeches, and the tool can enable you to measure how much is the risk of identifying the presence of certain documents in the training set, given how many sentences you already know about that document, right? So if you have samples from speeches of an author, as that number increases, we see that the privacy loss goes up, and it's very easy to identify whether certain documents were there in the training set. This is crucial, especially for organizations when there are lots of sensitive documents around. And something which is very interesting, and the tool can also provide that, or similar tools should provide, is to highlight what data points in the training set were more vulnerable than others, right? So here it's interesting to see that the data points that were more vulnerable to this attack were the ones that are also sensitive in terms of the content. So they stood out compared to other talks which are more about typical topics. Another example is on large image classification tasks, and we show that as the models get larger, as the capacity of the models get larger, and they get better in terms of the error in the classification, the privacy goes down, right? So there are more data points that are memorized. Here is not my objective to show more scary examples, but actually it's possible to exploit these risks to reconstruct images, and it is very worrying to see that that possibility. So I want to wrap up here, basically by highlighting again that enabling access to models trained on sensitive and personal data is not much worse in terms of the privacy risk than allowing basically access to the so allowing access to the models is not worse than allowing access to the data trained and which would be used as a training data for those models. So we have to put together a comprehensive privacy auditing framework that allows process-based auditing and quantitative based auditing of privacy risks Given that also there are many mitigation techniques around, we want to be able to have use a standard technique to compare different mitigation techniques. So privacy meter is a very good tool that can help. But I'm sure that in the next few years there will be more efforts. There are already ongoing works on expanding these kind of works, this particular tool, but also the others, and developing procedures so that DPOs, DPAs can actually benefit from these kind of quantitative measures. Thanks a lot. So I stop here, and if there's time for questions, I'll be happy to take questions. Otherwise, feel free to email me, and then I'll be happy to continue conversations with you.